Like 4 or 5?
No, not that many.
Sure.
I'm pretty sure.
Okay.
Is that what you think that's?
All right, here we go. Okay, here's one of these where it's an economics problem. They're giving us some information about, I want to explain this to you a little bit. This is interesting. We'll get a little economics lesson. And not stupid qualitative, it's quantitative economics, where we do the actual math. A university is trying to determine what price to charge for tickets to football games. At a price of $20 per ticket, they looked at their attendance figures, and attendance averages 40,000 people per game. Every decrease of $2 adds 10,000 people to the average number, at least over a certain number of decreases. Every person at the game spends an average of $5 on concessions. What price per ticket should be charged in order to maximize revenue? Okay. So you see, well, no, but you see what the deal is here. As you decrease ticket price, of course, as price goes down, demand goes up, right?
Right.
And so you got to figure out where in that mix are you going to get the most revenue.
So we're trying to optimize it.
Trying to optimize it, exactly. Okay, so we got to come up with a revenue function. Now, when we do stuff like this, there's a function, revenue, a lot of times is set up as equaling x times p of x. P of x is what we call a demand function. Okay, P of x, this is in this case the price per ticket. So P usually stands for price. Okay, so this guy is the demand function. We've got to figure out, what is the demand function? The demand function is going to come from the information about the price per item. So $20 per ticket averages 40,000.
But the question is revenue function.
Yes.
R is revenue, right? And revenue, of course, is going to be the number of tickets X times the price per ticket P, right? That's how much money we're bringing in. Actually, that's not the whole story, though, is it?
No.
Because in this case, we also have this $5 in concessions that we're bringing in. So where's that going to come in? Average of $5 per person. How many people are attending?
Wouldn't you put that in the P function?
Well, it's not in the P function, but it's going to be, we can add to it 5x, right? If x is the number of people, then 5x is the total amount of concession revenue. So there's two parts to that revenue. There's the ticket revenue and the concession revenue. So the demand function, first of all, for tickets. We got two data points here. We've got the $20 per ticket, 40,000 people. Every decrease of $2 adds 10,000 people. Now, here's what I like to tell people to do on this. We're talking about a linear model for our demand function. Think of it in terms of a graph. Okay, so let's just make a little sketch of this of the function, and you'll find after a while you won't even need to do this, but it helps a little bit. So let's graph P as a function of, how do I do this here? Doesn't really matter. $2, 10,000 people. So let's have, we'll put X on this axis, not that it matters, and P on this axis. Okay? Price and number of people. So we got one data point when X is 40,000, price is $20 per ticket. Those two go together, right?
X is price or P is price?
X is the number of people, P is price.
C for cost.
Well, okay, C is cost, but this is within the revenue function. This is what we call the demand function, the price per item. And cost is different. When we say cost in economics, we're talking about outgoing money. Right? I mean, that's specifically, we're talking about a cost function. That's the money the company is paying out to do business. Price is what we're charging the customer per item, right? So there's a difference there. So P for price. And if we look at this data point, then we've got one at X equals 40,000, Y equals 20. So we'll just put that arbitrarily right there. So the coordinates of that point are 40,000 and 20, right? We got another point. every decrease of $2 per ticket adds 10,000 people. So that means, let's just take one decrease.
18 and 3,000?
That'd be $18 per ticket and 50,000 people. Right? We're adding 10,000 people. So we're going to have another data point out here somewhere with coordinates 50,000, $18, right? And what we're looking for is just the equation of that line through those points. But it's just a line. It's no big deal, right? So we know that the slope of this thing is what? Right, we're from this point to this point, our rise is
like 5,000?
The rise is $20 to $18, so negative 2.
Negative 2 and negative 1,000.
The run is
10,000.
40,000 to 50,000, so 10,000. So there's our slope. So we know M is just negative 2 over 10,000, so negative 1 over 5,000. Okay, there's our slope. We know we have 2 points. Take your pick. Doesn't really matter. Let's use this one because they're rounder numbers. So if we take these to be x1 and y1, we plug those in for x and y to find b. How about? Okay, we got the equation. Y equals mx plus b. We could plug in. Here's our y. Here's our x. There's our m. That's kind of hard to see, isn't it? There's our m. Plug that stuff in.
What is the significance of b here?
Those are bad colors. Let's do those again.
Wait, what's the significance of b?
B is the p-intercept.
Well, I know that, but why is it important?
Well, it's important. I shouldn't put a y there, should I? I should make that a p. P equals mx plus b. Because we need to know what the function p is. We're trying to find this demand function,
Okay,
p
so
of
we're
x.
just trying to, okay.
Right? We want to find the equation of this line. So ours looks like p equals, let me rewrite that. P equals mx plus b, right? So if we plug that stuff in there, here are my lines. 20 is p, 40,000 is x, and negative 1 over 5,000 is m.
50,000 x.
Say that again?
Why not 50,000
I put in 40,000 for x.
B is
Well, I have to pick one point or the other. It doesn't matter which one.
So 50 or 18 or 40 or
40 goes with 20, 50 goes with 18. Either or would have worked. Both would have been fine. So if I put those in then, I get 40,000 equals negative 1/5,000th times 20. So 20 over 5,000 is 2 over 500, which is
Negative
1 over
8.
250. So negative 1 250th.
20.
Why is the 40,000 on the?
Yeah, you have that backwards.
20 equals 1.
Yeah, you have that backwards.
Oh, I got backwards. Whoops, I'm sorry. Yeah, you're right. Okay. Good thing you guys are paying attention. So 20, right, 20 equals
40,000 times
M.
100
So negative 1/5,000th times 40,000.
is negative 8.
So, right, negative 40,000 over 5,000. Cancel the zeros. Negative 40 over 5 is negative 8. Plus
B.
B. So what's B?
28.
28. Okay. So what we get from this then, we know our demand function. So we know then that P of x equals negative 1/5,000th x. So x negative x over 5,000 plus 28. Yeah. Yep. Okay, so there's our demand function. That predicts, that's how the price is linked to the number of people attending X. Okay? So, right, it's price per ticket as a function of the number of people attending. Right? So it's a function within a function here. So now we can plug this stuff back into our original. So our real goal here is this. Right? So let's go to the next page with that. How about it?
Where's this 5,000? Negative x over 5,000.
Negative x over 5,000, that's just M times X. M is negative 1/5,000 times X. Okay, plus B, we discovered B was 28. So if we plug that into our function, then we've got our demand function. Okay? So then our original revenue function, let's put it down here, how about? R of X would equal X times P number of tickets times the price per ticket. And then we also have that concessions bit at the end, plus 5x. So there's our revenue function, right? And the domain would be pretty easy. What's the domain?
Everything but positive numbers.
Positive numbers up to, I guess, the capacity of the stadium, which we don't know. So it's, is that what it is?
78.3.
I'll take your word for it. So it's 0 up to 78,000. Yeah, I don't know what it is. But I think our number is going to be, we probably don't want to put that there because we don't know. Maybe we need to sell more than that. This is,
Just put 100,000.
thing is we don't know.
Why not a million?
Yeah, why not a million, right?
Thing is we don't know.
Your arbitrary numbers are confusing me.
I'm just going to put that.
Ooh.
And it might be that, what if, that's still helpful to us. What if we find out that the, I mean, we're not going to, but what if we find out that the optimum number of ticket sales is 1 million? Well, that's telling us just try to sell out, I guess, right? I mean, you can pick the price that's going to, that would correspond to a sellout and charge that much. Charge as much as you could to sell that many tickets.
So for free.
But that's not going to happen. We'll see that's not going to happen.
That's honestly for me.
Yeah. It is. Okay, so let's go to the next page and do the calculus. The main part of that domain, obviously for us, was just that it starts at 0, right? We have to sell, that's 0 people up. Oops.
Is that the last problem?
Mr. Earl,
Yes.
are you going right now?
Yes.
Okay, because I have to go to the
Okay, go ahead. Good thing we got that on. Okay. That's very British. Okay, so what's our... So R of X then would equal 28, I'm going to put this minus term second, minus X squared over 5,000 plus 5X. I just mixed up the terms.
Are we going to end up setting it to 0? And
Well, we got to differentiate, right?
Oh, okay.
Okay, yes ma'am.
What is the 28 to me?
28X. Is
Yeah, there you go.
Hang on.
Plus.
Let me undo that whole step.
Yeah, you did that wrong.
I did. If I distribute the X, I'm going to get negative X squared over 5,000 plus 28X plus 5X is what?
Plus 32, 33.
There we go. Plus 33X. Okay.
When-
That's better.
So 2 over 5,000 is 2,500. Negative 2,500x plus 33.
Okay. Yeah. So let's differentiate this. So first derivative, R prime of X
Negative 2,500.
equals, now derivative of 33X is positive 33. This is just a little, this is what I always do with that. I'd rather not start with a negative coefficient. It's awkward. So why not put the 33 first?
Oh, yeah.
And then do a minus,
the 5
right?
on the end, and then
What's the
28.
derivative? What's the derivative of X squared over 5,000?
Negative 25, 1 over
Well,
2,500.
2x over 5,000, right? Which is 1x over 2,500 if I reduce the fraction. So minus that. Agreed? Okay. So if I were to, while we're at it, if I were to take a second derivative,
Just ignore it.
what's it going to be? Derivative of 33 is 0. Okay. And the derivative of x times negative 1/25, the x just goes away, right?
Negative
I just get
20
negative 1
over 2,500.
over 2,500, which most importantly, we don't really care about the number,
Negative.
is negative, right? Now, what about, okay, let's, Okay.
So it's, okay, that's just a negative equals.
It looks like an underline.
How about that? It's negative.
There you go.
Okay.
Okay.
So then, where is the zero of this thing? If I set this equal to 0, that's easy to solve. That's going to be 0 if I add this term to the other side and then multiply by 2,500 to isolate the x. Don't I just get x equals 33 times 2,500, which is
82,500.
75,000 plus 7,500, so 8,250.
8250 and another 0 as well.
Right, with another 0. 82,500. So that's how many tickets we'd like to sell to maximize. That's a big stadium.
So 78
It's rather large.
78 would not have been big enough. Good thing we didn't listen.
Hey, good job, Lane.
Big number. Okay? Make sense? Okay?
So that's the answer.
So that'd be the perfect amount of people.
Yeah.
That's the amount of people. What was the?
Also, if we want to set price then, okay. Well, that's okay. If we want to know what the price per ticket is then, because that's what we can control, right?
Yeah, can we just plug that back in?
Plug it back in. So we'll just go back to our demand function right here. There's our demand function, and we would just plug in 82,500 for X, and that would find out the price that we would set for that. Okay?
It's $11.50.
$11.50 is what we set tickets at. Okay? To maximize revenue. And what's if you did an economic analysis of this, if we looked at the parts of this function, what ends up being pretty important here is that $5 concession fee.
Yeah.
Yeah.
That's what's pushing that up. Otherwise, that wouldn't have been so high.
So why don't they just hike up the prices and concessions?
Because then you wouldn't get people.
Okay.
People spend an average of $5 on concessions. So evidently, it's not. If you hike them up too high, maybe they won't even go.
Just talking about
Yeah.
For X,
Raise
That's
everything by
X,
6
and that would
cents.
give us the price.
So we're doing like $1,000 more.
Price, yeah. Price per ticket is we have that function, the demand function, right there. 82,500.
Why don't they just hike it up by like 5 cents every game?
Well,
and
that's
see
going to
which
be
one works best?
your job as a high-paid quantitative economist to figure that stuff out for the
No, he's
company.
gonna be an actuary.
Oh, or an actuary. Then you're going to figure out what are the odds someone's going to slip on coke and crack their head. So yeah.
End up with you.
Okay, so
What
what about this guy? Let's at least let's just set up this. Yeah, we won't do this whole thing. Let's just set up the primary equation. Okay?
Yeah, we can't do this in half an hour.
Oh, we could. I want to move on to some other stuff too.
Oh.
Okay, so I mean, if we wanted, we could finish the whole thing, but you'll tell me if you
Why don't
want.
we just do it real quick?
Okay, find the volume of the largest right circular cone that can be inscribed in a sphere of radius 14. Okay, so it's three-dimensional. Here's our three-dimensional cone inside a sphere. Now, what they've done here, notice, is, well, have they?
You've drawn us that picture.
Yeah, they've drawn us a nice picture.
Yeah,
Okay,
it's fairly good.
so that helps. That helps a lot, actually. So we got to come up with the volume of a cone. Now, does anybody remember what the volume of a right circular cone is?
Height times pi something. 1/3 pi r squared.
1/3 pi r
Cube.
squared
Pi-
h.
Are you sure it's not cubed?
Yep. Well, that'd be fourth dimensional stuff.
Yeah, of course. We're not going into that.
That's r squared times h is going to give us volume units, right? Cubic units. Okay, so 1/3 pi r squared h. Problem, of course, being I've got two variables there, right? So in our drawing, what are those going to be? What is the radius?
14.
Well, in our drawing up there, what are we calling r?
14.
The radius of the of the radius of the cone. I should be more specific.
X.
X. Yeah. So we're talking about the cone here. It's the volume of a cone. So our equations, we're going to plug in
X.
x for r. Now, what's the height?
Y plus 14.
Okay, good. It's going to be y plus 14. Okay? So then our formula would become v equals pi over 3 times x squared times y plus 14, right?
Yep.
Okay, but we got two independent variables, so we need to come up with some secondary equation, which is going to be our equation of constraint. Okay, now what's the, and this is the part that I just think, I'm sure I don't know a way to emphasize this enough, because I think this is so cool and so interesting that the math follows just your logical way of thinking about this. What's the constraint? What constrains that cone? The sphere, right? The sphere does. And so that has to show up in the equation of constraint, because that is the physical constraint or the geometrical constraint. Well, here it is, right? This is the radius of the sphere. The radius of 14 is what constrains this thing. The radius of the sphere is what determines how big that cone can be.
Right.
So 14 has to be related to the other two variables, and there it is, very plainly in that right triangle.
Is that hypotenuse?
Right? It's the hypotenuse of the right triangle. See that?
Yeah.
I just think that is so cool that you just know, and that's the kind of thing when you go up about 10 levels from here in math and physics and things, and that's the way you think
Don't
about
worry,
this
I'm
thing.
not going to go that
Oh, you might.
I'm going into engineering.
10 levels.
Yeah, 10 levels.
Well, I just made that up.
What is 10 levels?
How about
You go up
let's
some
go with
levels.
4 levels.
Anyway,
How many levels have we crossed this year, first of all?
anyway, what you got to do, you get to a point where the math starts to get
Yeah.
the math starts to get really daunting. But what the math represents oftentimes isn't so daunting. So if you kind of think about now, what's the math representing? What do I have to do conceptually? And now I got to figure out mathematically what that means. That's how you got to approach more complicated problems. So this is a good model. It kind of takes us ahead a little bit in terms of what you'll be doing in the future. So we've got to take this little right triangle here, and it's a pretty obvious equation of constraint. X squared plus y squared equals 14. Now, which one are we going to solve for here?
14 squared? Question mark.
Which variable are we going to choose to substitute? Now,
When-
be
when
careful
you-
with this. This is important. This can save you a lot of work.
Why?
Because if you choose the wrong one, it can make the calculus
No.
much more difficult.
He was suggesting
Oh.
the variable y,
Oh,
but
okay. Okay, whoops. Gotcha. Okay, so we could do y, but I would say no, let's not. Because if I solve for y, that's going to give me a radical. I'm going to have to plug in a radical for y. What should I do instead? X
question.
squared.
Yep.
Yeah, okay, so hold that thought 1 second. So look, I've got an x squared there and an x squared there. See what I mean? If I make that substitution, it's
Single
much
variable. Yeah.
single variable, but it's a much cleaner substitution, isn't it? I don't have to deal with the radicals. Yeah.
Is your Pythagorean theorem not a squared plus b? There you go.
Sorry. Yeah. Okay, so then we're gonna solve for x squared. That's easy, right? X squared is just 14 squared, so 196 minus y squared. And I'll just put a box around it because that's our substitution equation. And then that goes in there. And then it becomes a really pretty simple equation. It makes it much, much easier that way. So we end up with, as a result of doing that, we get
Pi thirds.
v equals pi thirds times x squared, which is now the quantity, 196 minus y squared, times y minus 14. How about that?
How about that?
Squared. No,
Plus 14.
plus 14. Whoops, sorry. There we
There
go.
we go.
Okay? And then, now another question, another important sort of practical question here. When we've got a function to differentiate, do we want to differentiate that as a product, or would we go through the hassle of expanding out that polynomial?
I would expand it.
I'd expand it too. It's not that big a deal to FOIL that out, and that makes a polynomial, which is easy. Those are the easiest kinds of creatures to deal with in calculus. So we'd end up then with v of the variable y
Features.
equals pi thirds times, if I expand that whole thing out, I'm going to get
First,
let's
Negative
see,
y squared
196 times 14, that's going to be what, 1960 plus 392 twice, so what do we got, 786, 19, so...
come on, you're cheating now. You'll write it down.
I don't really want to have to write it down.
It's 2744 if you want that.
All right.
Yeah.
2744?
Yeah.
Oh, yeah, 6 times 4. Oh, my God. Yeah. Oh, I see how I would have messed
Rookie.
it up. Yeah.
2744.
Kinda like
So
see if I
you gotta
can-
erase that 7 too, boss. 2744.
44.
There you
You're kind of embarrassed.
go.
Okay, let's see
You
then.
can't multiply triple digit numbers in your head.
So plus 196y minus, what am I forgetting here? So I got those guys, I got those guys, I got these
First, you need your first negative y cubed.
guys. So I'm going to get minus 14y squared minus y cubed if I just did it backwards. Is that right?
Yeah. Got your first, you got your outsides, you got your
Got those guys, got
insides,
those
you got your
guys.
last. Yeah,
got
that's
those
good.
guys. Yeah, that's good, right?
Except you got them all and messed up.
Okay,
for
great.
it. But yeah.
Okay, just backwards.
Yeah.
So there's v of y. Okay, now while we're at it, real quick, what's my domain? What are the values of y that make sense here? Smallest value of y. This time we have definite limits.
It's greater than 0.
Okay, got to be greater than or equal to 0, right? Because if this thing, if we pivoted it out that way and made the fattest possible cone,
Right.
that would be the one that was straight across here, that had the equator as its base.
Yeah.
Right? And so that would be y equals 0, all the way down to the tallest, skinniest limit of a cone would be y equals 14. Right? And of course, 14 itself would be no good. So our domain, we could say then, might look something like
Less than
this.
0 to 15.
0 to up to, but not including 14. You could even
Yeah,
include
there you go.
14. Okay? Those are the values of y, or independent variable.
Right.
Okay? Questions on the domain? Okay? So now let's do the calculus. So might as well finish this. V prime,
Are we disregarding 5/3?
no I'm not, I'm putting it out front.
Okay.
Pi thirds times derivative of the first term.
Can we switch it backwards? Because that looks all. Never mind. Never mind. Keep going.
That one's 0, right?
Right.
Derivative of that one.
196 minus 28y minus 3y squared.
Okay, good. Right, and so the zeros of this thing are just going to be the zeros of that polynomial, right? Okay. So we could find the zeros. This polynomial equals 0 when negative 3y squared minus 28y plus 196 equals 0, right? Now, why not, while we're at it, being as we're going to use quadratic formula, multiply both sides by negative 1?
Sure.
Remember back to Algebra 2, I was harping on you about that? Okay, so this will be 3y squared plus 28y minus 196 equals 0. So let's go,
Are we going to be able to use our calculator so we can just plug that in?
yeah,
Okay, so it's 14 over 3.
yeah. Well, there should be 2 of them.
Yeah, negative 14.
Oh, plus and,
Negative 14 and 14 over 3.
okay. Well, we could just, okay.
Negative 14 is.
Does everybody see? We could, and that's fine. I'll let you use your graphic calculator. So you could just graph this thing or do the quadratic formula on your calculator. And evidently, if you do that, the solutions that we get are
Negative 14.
y equals negative 14 or positive 14 thirds. So we'll just take your word for that. We trust
So you
you.
don't trust me?
We trust you.
Okay.
Okay. What is the second derivative? We got a polynomial, so why not take the second derivative?
Why not? Negative 28 and negative. Negative 28.
So that's going to go away. I'm going to get, negative 28 minus 6y.
Yep.
More importantly, for any positive value of y, what's the sign of the second derivative going to be?
Positive.
Negative 28 minus 6 times y.
Negative.
Negative, right? It's going to be negative. So that's important for us to know. Now when we make our table, so we got a y, not x. We got y What are we doing, volume?
Yeah.
Yeah.
Okay, our domain went from 0 up to 14. We had a critical number at 14 thirds, right?
Right.
That was a 0 of the first derivative, and we had a negative value of the second derivative, so it's concave down. So what kind of creature is that one then, that extremum? Good. It's a maximum. Okay. So then if there's only one extremum on the whole domain and it's a maximum, that's got to be the maximum, doesn't it? That's the maximum
The
of volume.
absolute maximum.
Okay? That's the absolute maximum, yeah. So when y equals 14 thirds, that's our answer. Now what did they want to know here? They want to know the volume. So where would we go to find the volume?
Plug it back into the volume.
Yeah, we'll just go plug it into our volume function.
14 thirds.
Plug in 14 thirds and we'll get an answer.
You want me to do that?
Sure. Okay, make sense? Okay. All right, that's about as hard as it gets right there. Yeah.
Can you scroll back up?
Yep. Okay. Well, it's some answer. I guess we don't need to know what the answer is. All right. Let's take a quick look, and maybe we can wrap this up today. I want to take a look at maybe a couple linearization problems. You tell me when you find one you want to do. Find the linearization L of x at x equals a of some function. Now, remember, all this means, linearization is just a highfalutin fancy word that just means the tangent line. That's it. It's just the equation of the tangent line. The tangent line acts as the linear model of the function, right? Remember that if I've got some curvy function, locally speaking...
Y is H. No. Yes, Y is H, 14 is R.
Okay, so if...
Yeah.
If this is the value where we're trying to find the linear model, the tangent line's only going to be a good model, locally speaking. It's not going to be good out here. It deviates too far from the function. But locally speaking, for small changes in x, or whatever the independent variable is, it's okay, right? So a problem like this, all we're doing is we're calculating we're just going to calculate the equation of the tangent line. So there's f of x, there's a, right? So then we know that the y value of our point of tangency is just going to be f of a, right?
What is linearization?
Well, that's I think you were going for that. That just means when we're making a linear model, we're using a linear model to approximate the curve,
Okay.
the tangent line. So that's just going to be 4 times 2 cubed plus 3
plugging in
times
A
2
for
plus
x.
1. So what is that? 32 plus 7 is 39. Did I do that right? So there's the y value of the function. The x value is 2, right? To find the equation of the line, we got a point. Our point is at 239, but we need a slope. How do we get the slope?
Plug it into y equals mx plus b.
Well, okay, but to get the slope of the tangent line is just going to be f prime of a, right?
How do you...
So the derivative of the function,
Is
Right, that's f of
wouldn't it be
x.
f of x?
f prime of x is what, 12x squared plus 3?
Yeah.
So f prime of 2, a is just 2, isn't it?
Yeah.
f
So to
prime
put
of
2
2,
in. It'd be 52.
yeah, good, 12 times 4, 12 times 2 squared plus 3. So that's equal to, what did you say it was, 51?
Yeah, 51. So that's your slope.
So there's the slope,
And then you gotta find your p.
there's the point, find B and you got it, right?
That's it?
That's it.
Where'd the 12
The 12, from the derivative, right? We had to take the derivative of the function, and then to get the slope of the tangent line, so the slope of our linear model is just the value of the tangent
That's it.
at x equals 2. Right? So that's we've done that a ton of times way back earlier in the year. That's no big deal. Okay? All right, moving on. Oops. Okay, approximate the root. Okay, yeah, how about this one? Now, I think everybody can do this, but the question is, how do you know which one of these is right? I'm not sure if I'm even going to grade that.
Oh, I know which one's right. It's,
Yeah, it's
C. C is right.
Yeah, it's C.
C is
It's
right.
C.
It's C. Okay, well, let's see if you're right. Let's check.
Actually,
How many times have you tried this?
C is correct.
I'm pretty sure it's C because they
Okay,
always
can
say-
you just run over this real quick? Because I don't know why you're burning out numbers. I don't know what the hell is going
Oh,
on.
it's just because I've actually not 100% sure what I'm assignment. I think I just saw a pattern that I left. And I clicked it right, and I kept clicking it without really.
Okay, so square root of 83, right? So remember what we do with this.
I want to know. Okay, whenever you guys are ready.
Okay, so the Math Excel book does this a little differently than we talked about. Remember what we said was when we want to do a linear approximation, it's always the same. We know that the absolute change in the function delta y is approximated by dy, the differential. And the differential is always just defined as f prime of x dx, right? And so what we would do on this problem is we would write the square root of 83 as the square root of 81 plus 2.
So 9 plus root
Okay?
2.
And so our approximation here is going to be, what we're saying then is that f of x plus dx is approximately equal to
9 plus root 2.
f of x plus the incremental change in the function, plus dy. So f of x plus f prime of x dx. Right? We're going to pick a convenient point to evaluate our function at, and then we're going to estimate how much the function changes, how much dy is, the incremental change in the function when we scoot over in the x direction by dx. Right? And this is what the change in y from our convenient spot is always going to be estimated to be. So another way of thinking about that would be like this. It's like saying,
So we have right there.
that's all it is. It's the value of the function at the convenient place plus our estimate of the change in the function. Okay, but that's how we want to write it. So then if our function in this case is, we're looking at a square root function, aren't we?
Mhm.
Right? F of x is the square root of x. So if f of x equals x to the 1/2, f prime of x equals 1/2 x to the minus 1/2, right? Which is nothing more than 1 over 2 times the square root of x. Right? And so if we evaluate this thing at x equals 81, right? So for our problem, we know that x is 81, and what's dx? How far have we scooted away from our convenient value? 2, positive 2. Right? So we're going to get f of x is the square root of 81 plus f prime of x, that's going to be 1 over 2 times the square root of x is 81 times dx.
Did you say you are going to avoid this question from the test?
No. You just weren't here for this stuff. So on the top, dx is just 2, right? So that's what this is going to give us. Now, which one of those things does that correlate to? That's going to be 9 plus, let's see, that gives us, in our case, see, this is a dumb way to write. X minus 81 is 2, isn't it? Right, so that's going to give us 2 over 2 times 9 is 18. So it's got to be this one, doesn't it?
This one over there.
Because, and that's kind of a dumb way of writing it, but that's 2. That's our dx. Okay. I'll tell you what, on those, if you get the top one right, I'll give you a single bonus point. If you get the, I don't care if you get this one right, though. All I care is that you
get extra credit?
You get that answer. 1 point extra credit. Woo! That's the only extra credit.
Good, because I didn't understand a damn thing you just did.
But this is the one. This is the one I want you to get. I want you to get the right, wrong answer. I want you to get the approximated
All you have to do is
answer.
plug it into the thing that you got on top of, don't you?
Which all you have to do is plug it in. Oh, true.
Life is relative.
But no, if you put in the square root of 83 in your calculator, you're going to get the correct answer, which is wrong. I don't want the correct answer. I want the approximated answer.
He wants it to be wrong.
Yeah.
Yeah.
Yeah, then you have a failure.
I don't want you to be correct.
You know, the right answer is always the wrong answer.